So the last situation we want to look at is when we slice things horizontally. So slicing horizontally. And this comes up, especially in pictures like this one. We'll skip down. If you were to make vertical slices for this region, which is fine, you run into a little bit of difficulty because if you want to do top minus bottom, you have to subtract the y coordinates, right? Keep in mind, if you were looking at 2 points, right, and this was at, I don't know, 2, 8, and this is at the point 2, 3, you subtract the y coordinates, not the x coordinates. So you have to know what y equals. But if you look at these points, what does y equal here? Well, gosh, this is hard to solve for y. Not to mention, they're on the same curve. So if I have y equals the blue minus y equals the blue, don't I get 0? Like, this is a big mess, okay? Now, there's ways to work this out, but it's very, very hard. Sometimes it's actually impossible. So when you have a situation like this, we're going to try a different way. One of the hallmarks is that this function is not defined as y equals, but it's defined as x equals. That's a hint that you want to use this technique I'm going to show you. So instead of doing vertical slices, we're going to do horizontal slices. And again, these are really little rectangles. And I'm splitting the area into little rectangles. And I'll figure out how big each one is and I'll add them up. So in this case, the length is not top minus bottom. I have to figure out what the length is. So if you have a horizontal line segment, let's say going from the point, I don't know, 3, 4 to the point 7, 4, I need to look at my x coordinates. So when I do length, I need to know what does x equal on the right and what does x equal on the left. I also need to do right minus left to make sure I get a positive answer. The bigger x coordinate is on the right, the smaller x coordinate is on the left. So in this case, I know what these x's are. Do I know which is which? Let's look carefully. This red one is a sideways parabola. So this red graph is this one, which is a quadratic. The blue one has an extra curve right here at the end. The blue one has an extra curve right here at the end. So you can tell that's cubic. And this is the blue curve. So when I do right minus left, I'm going to do the blue curve, x equals y squared, 12y squared minus 12y cubed, minus the left-hand endpoint, x equals 2y squared minus 2y. Okay, so a lot of this is written out above, and then we'll come back down and do this. So up here it says you're going to use horizontal slices. The height of the rectangle, which is horizontal, we're going to use the right minus the left. The right-hand x-coordinate is x equals 1 function. The left x-coordinate is, that's a typo. The left x-coordinate will be x equals a different function, and then you're going to subtract those. Again, one thing to note, we talked about the length of the rectangle, but what's the height of this rectangle? The height of each of these rectangles is very, very small. It's really the change in y this time, or a dy. So this is how it comes together. To find the area, I'm going to add them all up, okay? So to find the area, I'm going to take the length of the rectangle, which is right minus left. Okay. So this is the length. And the height of each rectangle is a very, very small delta y, or a dy. And then I have to add up all these rectangles. And the rectangles go from the bottom to the top. So instead of going from an x to an x, these are going from a y to a y. These are going from y equals 0 to y equals 1. And it's great that they're y coordinates, or y values, because that matches that this is a dy. So then again, you evaluate this either by hand or using a graphing calculator, and that's how you do the problem.